Honored to be here to present on the work that we're doing at the Alberta Biodiversity Monitoring Institute. I've been involved with the ABMI for the last 10-15 years. The goal of that program is to provide information that folks can use, and by folks I mean government people, industry people, or the general public can use to make better management decisions as we're doing things in the environment. So it's to help folks evaluate what the consequences, what we're presently doing, and at least predict some of the expected future consequences if we do different things in the environment. Today what I'm going to do is present an overview of the program, so a brief overview of the breadth of the program, and then the last half of the talk get into some fairly specific, I'll call them uses. So things that we've worked on in the last 5 or 6 years on things that we think are emerging issues where we can use information from the ABMI to help make better decisions in land management decisions. So, first of all then, the ABMI, the goal of the program when we started was focused mainly on goal number 1, to be able to track and assess ecological health at the regional or provincial scale. So note, what is the status of biodiversity? What is the status of ecological health in any given region? And a region, think of a region about like that as a region. So what is the health of biodiversity? What is the health of an ecosystem in a region or the province as a whole? In the last 5 years, we've realized we can do a lot on goal number 2 as well, which is to be able to assess what is ecological condition, not in a region, but at a particular site. So think a quarter section when I'm talking about site, or 100 hectares, or maybe even down to 50 hectares. But what is the ecological health, what is the ecological condition at a very local scale? So the program's meant to tackle things at a variety of different scale, all based on ecological health. The kinds of things that we look at is broad. We made a decision in the program, early on in the program, we made a decision, we said, rather than trying to choose what are the key 4 or 5 or 25 things that people are interested in, let's go for breadth. If you cast your mind, sadly, there's a lot of people in this room who can do this. If you cast your mind back 50 years ago, you couldn't predict today what we're presently doing. You couldn't predict then what we're presently doing on the landscape. You just simply couldn't have predicted it 50 years ago. So what gives us the gall to think that we can choose things now, expecting to then say they're going to be relevant 50 years from now? So rather than going for specificity, we chose to go for breadth. So regardless of the kinds of things that we choose to do in the future on the landscape, some of the things that we sample will be expected to respond. So we went with a variety of different things to include in the program. Ordinarily in the program, folks deal with vertebrates when you're doing monitoring and vascular plants. If you looked around the world at monitoring programs, so what kinds of things people monitored when they're monitoring ecological integrity or biodiversity or ecosystems, people deal with vertebrates and vascular plants. That's it. There's a lot more than vertebrates and vascular plants that live in Alberta or anywhere. We purposely chose in the ABMI to be broader. In addition though, we said there's a few constraints on broader. We want a group of things, so we get many species, but they needed to have some sort of characteristics. They needed to be good statistical things. it's darn hard to detect, to assess status and detect change in an ecological system. We need to monitor things that have a good signal. Excuse me. In addition, as one gets to an integrated program that has a wide variety of things involved, it costs a lot to do the sampling. So we wanted to include things that we could put together into an integrated program. And finally, we threw in vertebrates, not because they have any redeeming features, but because society demands it. So everything else in the program is there because it makes sense. Vertebrates are there because we had to. The program, and this is an overview then of where the program ended up after 4 or 5 years of development. So in the late 90s, early 2000, 2002, there was a group of 30 or 40 academics who met off and on, and this is where we ended up. So the program is a series of sites. Each of these little red dots is a site. There's 1,646 of them throughout the province. Some of you may be aware of NFI. These are the NFI sites. That NFI stands for National Forest Inventory. So there's 1,600 sites. The goal is to survey a fifth of the sites every year. We're not there yet. We're still ramping up. To survey a fifth of the sites every year. So after 5 years, you'd be through one complete cycle and then start again the next year on the sixth year back at the start of the program again. So it's a rotating panel design. In addition to these little red dots, we survey a whole bunch, and I mean a whole bunch of off-grid sites. And that wasn't the plan originally, but it became obvious that all of the modeling, all of the statistical analysis we're doing required the ability to expand the x-axis, expand the predictive value on a variety of different things. Think on the amount of different habitat types or the variety of different disturbance types. So we sample, in addition to these on-grid sites, a wide variety of off-grid sites just to make the analysis better. What did I do there? Something I shouldn't have. In addition, the goal of the program is to be able to detect a change in the ecosystem of 30% if such a change occurs. That's a hard goal to achieve, but it is the goal of the ABMI. Excuse me. So at each of the sites, then we do some remote sensing around the sites and then on-the-ground field sampling. The remote sensing is your typical remote sensing. This is an ICONUS image, and this is a composite of a couple of air photos. So typical air photo remote sensing type of information. And then on-the-ground sampling, centered on the site, so a yellow star, but the spatial layout of the sampling depends on the taxa that is being sampled. So for instance, for birds, we do a series of point counts with the point counts separated by 300 meters. So we just used the sampling that made most sense based on the taxa that was being sampled. For mammals, again, there's the yellow star, but mammals is sampled along a series of transects during the winter, and we do snow tracking samples, and these transects for mammals are 10 kilometers long. Many of the things that we sample that are small and immobile, plants aren't small, but they're immobile, and mosses, lichens, mites, those we sample very close to site center. So site center again, but this now is within a 1 hectare area. We sample a variety of different taxa right in there. You'll notice that the goal here is to get that integrated sampling design. Reduce costs. Along with sampling the critters, we also sample a variety of characteristics of the habitats. Trees, logs, soil, that sort of thing, litter. That is that broad grid design, those random layout of sites. it became obvious, well, it was a given fact before we started, that if one samples randomly, there isn't really a lot of sampling in wetland areas. You just don't hit wetlands if you sample an environment randomly. Now you do hit a few. It's about 6% of the province is a wetland. Well, that's a wetland with water. If you count bogs and fens, it goes up to about 20%, 22 or 3%. But you don't hit those if you just sample randomly. So what we said is we're going to go to each one of these red dots, which is the yellow star, and find the nearest wetland with open water. So each sample is really a paired sample. One sample at the yellow star and one sample at the nearest wetland with open water. And at the wetland, then we also do sample a variety of different things. There's characterization of the wetland, the wetland zone, the water, the vegetation around it, plus then sampling of the vegetation in zones around the edge of the wetland, aquatic inverts out in the open water, and water physiochemistry data collected out in the open water. But because we were interested in these aquatic inverts, we needed to choose wetlands that had water. So our paired sample always is a wetland with open water. In addition, I'd say we resisted, and we resisted because it's just stupid expensive. But we've been forced to move down the road of figuring out ways to incorporate fish sampling into the program. So sampling fish doesn't work near so well on a random or a systematic layout of sites. Fish are associated with rivers and lakes. So we have divided the province up into tertiary watersheds. That's these watersheds over here, the little black lines. So the primary watersheds and tertiary watersheds are shown there. And then for each tertiary watershed, we sample both the river systems, so both the main stem river and the tribs, and a lake within each of those tertiary watersheds. So fish sampling is not based on that 1,656 sites, it's based on 132 tertiary watersheds. It's quite a different perspective for fish than the others, but if you want to sample fish, you pretty much got to go where they're going to live. And they're living in these rivers and lakes. In addition, there's probably 15 crew days for each of those tertiary watersheds. So it's expensive. It really is expensive to sample fish. I don't know any way around it. We tried some stuff that wasn't expensive and we got really nothing for data. So you go back and say, well, I guess if that's what's required, that's what's required. This is where we are so far. So these are the little wee tiny black dots are the 1,656. The sites that have bigger dots on it are sites that are already sampled. The green dots are the ones that are planned for this next summer, so the summer of 2012. These blue dots here, we did a pilot study between 2003 and 2006. 2003 and 2006. And those blue dots were the ones that we sampled during the pilot. In the pilot, we only sampled some of the biota. So it was a pilot to see what we could collect, how easy it would be to collect things in areas that were hard to access, and how we could analyze the information. And it really was to roll things out and let folks see what we could do with the data. Think of it as creating information to allow us to market the program. So those first 4 years was all about getting information and using that information to allow us to build the bigger program. Since 2007, we've started to ramp up to the complete program, but we're not there yet. We're still only just over halfway to where we want to be on a year-to-year sample. 2012, our plan is now actually to sample 177 sites, so this slide's a little bit out of date in 2012. And since 2007, we've sampled all of the critters. So since 2007, we're implementing all the sampling protocols. In addition, in the last 3 or 4 years, we've done a lot of off-grid sites. And the off-grid sites really are all about analysis, and I'll get into that in just a bit. They became really, really critical to do these off-grid sites. So what we get then is a variety of information, and I'll run through this for you, but it's fairly intuitive. At every site, we get information on critters. Now think of this as meadowlarks. So at every site, we get information on whether or not the species occurs, and when it occurs, how abundant is it. Those two pieces of information we use to calculate the status of meadowlarks. Meadowlarks then simply become one of 15 species when talking about the status of short-distant migrants, or one of 100 species when we're talking about the status of grassland birds, or one of 200 species when we're talking about the status of birds. So it's a fairly straight progression as you move up through this pyramid. And you can combine birds with a whole bunch of other things when you're talking about the status of biodiversity. It's a fairly simple concept. What I mean by status, again, the concept is simple, the math isn't simple, and that's because the distributions are bad. I mean, they're silly. But the concept is fairly straightforward. These blue dots are sites, the actual sites that are measured. And by doing off-grids, we get to fill out this x-axis better than if we didn't do off-grids. The x-axis is the amount of human footprint at the site, all the way up to 80% of the sites disturbed by humans, down through to 0% of the site is disturbed by humans. The y-axis is the number, in this case palm warblers, observed at the site. And you can see that they always are observed in units of 1, 2, 3, and 4, because you never find 2.3 birds. You either find them as 1 or 2. And that creates a bunch of distribution problems. What one can do then is calculate what is the expected number of palm warblers when there is 0 human footprint. If one then samples a region of interest, so now these are red dots from a particular region. This happens to be the lower Athabasca region, and this analysis was done in 2009. So the red dots were from the lower Athabasca from the data that we collected by 2009. You'll notice that the observed in the region is slightly less than the expected in the region, and the status of palm warblers is simply observed over expected times 100, 38%. It's a simple concept. So, and you can do that for every species. And for any given region, you can talk about the status of the species, or you can lump it all the way up to talk about status of biodiversity if you like. And that's exactly what we did. This is work that we did in 2009 for the lower Athabasca region. And we talk here about the status of birds. This center line, I'll go like this. That line is 100%. Anything below the line means that it is less abundant than you'd expect under reference condition. If it's above the line, it means it is more abundant than you'd expect under reference. If it's more abundant, it still gets to be less and less intact. If it is less abundant, it is less and less intact. It's intact when it equals reference. So this is simply a way to present how do species change from that expected under intact conditions. And you can do that for birds, and you can do that for plants, and you can do that for habitats. And overall then, what we found when we did the analysis in 2009 was on average in the lower Athabasca region, the intactness of biodiversity was 94%. Since then, we've done the same sort of thing for a variety of other regions, and we will keep on doing the same sort of thing for regions. It allows folks to assess what is the present state of intactness, ecological health in different regions. This is where we wanted to be able to provide this information. This was a primary goal when we started the program. But everybody in this room knows that things have gone, that in the Northeast region, intactness isn't 94%. Well, I can tell you that on average it is, but on average doesn't tell you the whole story. So in the Northeast region, this part here, on average, if you looked at that green, the green says it's pretty high. But there are places in the Northeast region where intactness isn't 94%. So we knew that. But what we said is then we as a program need to find a way to present information so that folks don't look at it and say, huh? Give your head a shake, it ain't 94. Well, on average it is 94, but there are places that aren't. So how can we talk about those places that aren't 94% at the same time? And we, originally we hadn't planned on doing this, but it became obvious we should. So this next part is still in development, but we've made some good strides in the last 3, 4, 5 years. This is exactly the same data that I've talked about before. So it's all using exactly the same data, it's just using it in a different mathematical framework. Again, down at the bottom, we've arranged information from 0% disturbed up to 100% of the site disturbed by humans. On the y-axis this time, it is the deviation of the biotic community. So this isn't done at a species level. This is deviation of the biotic community from the average expected in undisturbed condition. So we've analyzed the data differently for this figure. The white dots, those are sites that are more or less undisturbed. Now we said anything up that has up to 5% human footprint, we'll put into that group. And you'll notice that there's some deviation. There's natural variation. More importantly, there's measurement error. Measurement error is a big deal in ecological sampling. So even undisturbed sites aren't all the same. Not even when you start correcting for covariates. There's a whole bunch of variation just in undisturbed sites. You just got to recognize that. So there's some deviation even back at undisturbed condition. However, as you get more and more human disturbance in the landscape, the deviation increases. So that by the time 100% of the landscape is disturbed, and this is just where the vegetation's been removed. So when we remove vegetation, think cut blocks or seismic lines, the biota are about roughly 50% similar to what undisturbed would be when 100% of the vegetation's been disturbed. If one disturbs both the vegetation and the soil, the biotic community is about 70% different than what you'd expect under undisturbed condition. So this then just provides a measure of how similar the biota are as you do some deviation, as we as people change the environment in which those critters are living. The neat part about this is you can use those kind of relationships. So this is the exact same data that I presented on the previous graph, just I'm going to show it in a slightly different format to ask specific questions about management decisions. So these little diamonds here are the ABMI data. And we said, so this describes the background of what we expect for deviation of biotic communities as we, as people, disturb the landscape. We then worked with a forest company, Alberta Pacific, and sampled some of their cut blocks that they cut about 15 years ago. And if you recall, LPAC does this structured harvest, so they leave a bunch of residual in their cut blocks and so on. So these are LPAC cut blocks. They may not be the same as somebody else's cut blocks. But what you'll notice is alpine cut blocks tend to have biota more similar to undisturbed than you'd expect based just on this line. Two things going on here. These are 15-year-old cut blocks. You walk into that cut block, the trees are actually this tall. It's not a cut block anymore, it's a new forest. So don't be surprised the biota are recovering. It's still disturbed, but the biota are starting to recover because the trees are coming back. In addition, they chose to leave a bunch of structure in their cut block, and that may have made it so that A, they didn't come down to this line to begin with, and B, they might have recovered faster. All I think of the take-home message is, one can use this kind of figure to assess different management conditions and see whether or not things work out well. Do that for many, many different types of habitats. I'm going to then go to something this is all hypothetical. We haven't done the work. I'd love to do the work, but we haven't done it yet. But it has applications for reclamation, for assessing reclamation success. And the concept is identical. It's just that one needs to collect some data in reclaimed areas before you can show that it's not just a hypothetical thing, but it actually works. So what I'm showing here is hypothetical. I made it up, guys. I say that. These dots here I didn't make up. Those are the same dots from the figure that I took before. But all that says is, under natural conditions, we expect some variation in biotic community. If we have a site that we're going to disturb, prior to disturbing it, we expect it to fall in that natural undisturbed group. You'd go and measure it and see whether it's true, but you'd expect it to fall there. After we disturb it by, say, putting in a mine site, the expectation is the biotic community is going to be quite low. Now, I don't know how low quite low is, but if you create a gravel pit where there used to be a forest, the biotic community is going to change. You don't have to think too hard to come up to that conclusion. Expectation is when you choose to reclaim the mine site, the biotic community should jump back, somewhat more similar to undisturbed conditions, and then over time, as things recover, you expect it to march back towards undisturbed condition. One would have to sample this point, this red point, and these green points to know whether or not you achieved any of this stuff. You can't just say it's going to happen. You need to sample it to do it. But what's neat is the ABMI provides this scale and these white dots to help you guess what undisturbed is. So you don't have to sample the white dots and you don't have to create the scale. All you got to do is sample the red and the green. It's a pretty cheap way to sample reclamation success when you're doing your sampling. So we think it's a huge tool. Having said that, we have yet to convince somebody to collect the data so we can do this analysis and show that it works. Although, I mean, it's a no-brainer. I'm 99.999% sure it's going to work. It's just we need to prove it up, darn it. The same thing, exactly the same idea, except the things that we're interested in work for conservation offsets. So again, it's this scale of 0 to 100. Again, for a site to be developed, we expect it prior to development to be in the undisturbed condition. After development, it's going to drop down. For conservation offsets, though, it's not reclamation. There's an offset site that is purchased, and that offset site is purchased in a developed area with the expectation of recovering the developed area. So you're not recovering the site that's disturbed, you're actually recovering a different site in a conservation offset. But the concept is the same. And then the expectation is you reclaim the offset, and then over time, the offset marches back towards undisturbed. Again, hypothetical. We haven't done the analysis. there's absolutely no reason that this wouldn't work. From a conservation offset perspective, one is interested in ecological loss here, the ecological gain from reclamation, and the ecological gain from reclamation plus recovery. But conceptually, they're not really that much different than reclamation. What the heck happened there? Oh, in addition, there's a bunch of things that come into play for conservation offsets that aren't in play when you do reclamation. So conservation offsets, because you choose to go to a different area, you have to then ask a question of how similar is the area that's reclaimed, or that's the offset, versus the area that's disturbed. So if the area that's disturbed is here, and the area that's offset's down here, ecologically those two areas aren't the same. We can use ABMI data, and this is information, I think the analysis was done in 2008. So this says, at the yellow star, how similar is the biota as you move anywhere else throughout the province? Not surprisingly, really close to the star, the biota are pretty darn similar, and as you get further and further and further away, the biota get different and more different. So if your offset, the further away your offset is, the more you would need, the more area you would need to get more or less the same biota into it. So it's just, there needs to be some sort of factoring in then of the degree to which biota change geographically. In addition, if your offset, so if the part disturbed was like this, and the offset was like that, you gotta recognize that the biota differ between those two habitats. So probably you need to include bigger offsets if you're choosing to use offsets that are in different habitat types. So offsets have a variety of additional constraints, additional things that you need to be worried about as you implement them. I'm getting close to my last the last topic I was going to tackle today, cumulative effects. And we have just started doing this in the last 2 years. In reality, it's only been a year since we've started to spend any time on this. And what we've said is we think you can use ABMI information to help do better cumulative effects assessment than we presently do in Alberta, or Alberta doesn't hold the cake on this. I think you can say the world. We, at present, don't do great cumulative effects assessment when we're doing developments. And as a result, we shouldn't be surprised that we don't succeed in managing cumulative effects because we don't do very good assessments of them. There's 4 steps in cumulative effects, and I'll kind of walk through them. First of all, to understand cumulative effects, you need to know what kinds of changes you're expecting to put into the environment. So this is the case for boreal chickadee, the amount of boreal chickadee versus the amount of agriculture that we put on a landscape. It's just, there's a relationship. There's some sort of mathematical relationship between abundance and amount of disturbance we put on. And that relationship differs depending on the type of disturbance you're doing. We can use ABMI data to calculate these relationships, not only for agriculture and roads, but we can do it for a whole variety of different things. Those things, then when we're done, and knowing how boreal chickadee vary throughout a region, one can predict then what is the present condition. So you use the relationships, these figures, plus density of boreal chickadee throughout the region to predict what is the present density of boreal chickadee throughout the region. This is a prediction. Nobody's gone out and measured boreal chickadee at every one of those pixels throughout northeastern Alberta. This is a mathematical prediction. Dark blue means there's lots of them, red means they more or less not there. But you can use the relationship here to make this map. And you can make it pretty darn rigorous. There's things that come out obvious. This one here, and those are mine sites. This is SAG-D kinds of stuff down here, getting into agriculture. It's pretty obvious. Boiled chickadee don't like any of those things. That's present conditions. You can also then, as long as you know what you're putting on the landscape, you can predict what is the expected future density of boreal chickadees. And it's the same thing. Now here, this is hypothetical. We said, what happens? We created a huge mine site right there. But we expect boreal chickadees to go down in that area. And this, based on these mathematical relationships, we can produce this map as well. What's really, 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 really neat about the ABMI is this kind of stuff people have hypothesized on before. Rarely do we have this kind of information to make good maps, but we make the maps even if we don't make them good. What we don't do is test to see whether it works. This is a prediction. It's like me telling you that next Monday it's going to rain. It might, or it might not. This is a prediction. It might rain, or it might not. With using the ABMI and continuing to sample, we can figure out whether it really did rain. Is where we predict the chickadee to go down, did they go down? And did they go down by the amount we thought they were going to, or did they go down by a different amount? So that over time, we get better at predicting, and we say, you know, this is not what we want to do for management. We want to try doing this kind of management because it seems to meet our needs better. So the ABMI, by doing the long-term monitoring, allows you to assess whether the predictions were true. So that's really just the 4 steps for cumulative effects assessment. We have the ability in Alberta to do this because of the ABMI. There is, I was going to say, probably no place, and that may be right, there's probably no place in the world where they have this kind of system, no other place. So we have the ability to do things that other folks don't. We aren't doing it yet, but there's no reason we couldn't do it. There's some neat bells and whistles. Those are the same pictures I showed you before. This white graph then is just the difference between pristine, so this is undisturbed condition, present condition, and this just says, what is the degradation at present? You can also then say, what is the expected difference between undisturbed and future? So that's the predicted degradation in the future. From a management perspective, you just ask, we're here now, are we comfortable going to here? It's a societal decision. The ABMI can't make that decision, but in spades, they can show you what the concerns are. And then it's up to society to decide. Maybe we like that mine site, in which case we're going to put the darn thing in, or maybe we don't. In addition, you can do some bells and whistles by scaling the boreal chickadee from 1 to 100, and then you can scale dandelions from 1 to 100, and then you can scale Swainson's thrush, and then you can get a map of biodiversity. And that allows you then to talk not just about boreal chickadee, but about the ecosystem as a whole. So, overall, I'd say we've spent a lot of time on this regional impactness, and I think we're getting there. We've started to talk about site condition and how we can do things at site condition and how we can help provide information that folks can use to make better management decisions. So the ABMI doesn't make the decisions. We provide the information that allows folks to make better management decisions. What's neat in my mind is this integration at the regional and the site level. You can talk about the same things at the site as you're talking about at the region. So if at a region you're interested in caribou, you can also talk about caribou at the site. If the region you're interested in downwood, you can talk about downwood at the site, or vice versa. So integration among scales is important. And I also stress, we really are just scratching the surface. We started down the road here, but the data set here is huge. And anybody that likes data, there's some really neat stuff here. Ending, one slide, this program ain't cheap. We knew we had to market it to get to make the program work. Last year, the program was about $8 million. This year, it's a bit more than that. But remember, we're still at about half of where we want to be. The program isn't cheap. The data we get is darn good, but it ain't coming for free. So we need to find ways to continue to be able to get the funding we need to get the information that we're collecting. That's it, thank you.
I was just curious as to how natural disturbance regimes such as fire, if those are included somehow.
So there's the analysis that I showed you, there's two major types. In the regional analysis, they are part of the regions are big enough that one can incorporate natural variation into the analysis quite easily. So the regional analysis is not near as much of a concern as the site level analysis. In the site level analysis, like any research kind of question, one focuses on the particular characteristics you're interested in. One can also, though, include covariates, and we've done a bunch of playing with it, and at this stage, think of it still as playing. So we've done a bunch of playing about how to include covariates to include a broader sample size in the site level analysis. But it is much less of a concern in our regional analysis than it is in our site level analysis.